All right, welcome back to Today we're going to talk about a parabola as a conic section. We're not going to talk about it as a parent function anymore. We're going to look at it from a slightly different point of view. Now you'll see a lot of the characteristics will cross over, but there are a few new components that we need to talk about. And additionally, we'll talk about the foldable pamphlet that I have for you, which will help you kind of compartmentalize everything that's on this set of notes as well. As usual, we'll take a look at the explorations tomorrow at the beginning of class. I don't know if we're going to do those yet. I tried with the protractors and they're not all that accurate, so it may not work out the way it should. We'll talk about that tomorrow once we begin class. Instead, let's go ahead and start with the vocabulary. The two new things that we have here with the conic section version of a parabola is a focus and a directrix. A focus is a fixed point on the interior of a parabola. If you want to think of this as a tangible object, you would think about a flashlight, where the flashlight reflective lens is a parabola and the light bulb itself is the focus. A directrix, it's just a line that is perpendicular to the axis of symmetry, and it is on the exterior of the parabola. Now, in the definition of a parabola as a conic section, the distance between the focus to a point on the parabola is the same as the distance from the directrix to that same point on the parabola. And that is how a parabola is formed. And we're going to get into that in just a few minutes with one of our examples that I'll do together with you. So now we're talking about standard form of a parabola when it is a conic section. So now we're introducing a new standard form, which is in fact different than the standard form that we've studied so far with the parent function of a parabola. So that's why this is a brand new type of concept here. And you'll notice right here in the middle is this value 4p. This value 4p is the key to solving parabolas as they are written as conic sections, because you'll notice here that the value of p is going to be the value of the focus as well as the value of the directrix. And it's always going to be the value or the distance from the vertex to the focus and from the vertex to the directrix. So once you've found this value p, you'll be able to solve anything you can or need to on a parabola. Now there is something that I'd like to add to this because we're going to need to know it later, and these are called your reference points. Now reference points are critical because otherwise there's no way for you to determine what the stretch or compression is for this particular parabola. The reference points are always located off of the focus, and they are 2p units, in this case left and right of the focus. So if I were to come over here, this distance right here is the distance 2p. This distance likewise from here to here to this point is also 2p. And these are known as your reference points. They're going to play a very critical role when we look at the stretch and compression of these particular conic sections. So now this reference point is going to be 2p units above and 2p units below. So let's go ahead and write that in so we can see the difference. Reference point. Again, that's 2p units up and down, and that is from the focus. So your reference points are here, 2p, and your reference point is here, 2p. And I'll label those RP. Very important, because otherwise you wouldn't be able to know the actual accurate stretch or compression on your conic section parabola otherwise. All right, so keep that in mind as we move forward. You'll notice here we have the same standard form, but now we've got a parabola which is no longer located at the origin. So now we reintroduce that h and k. So technically this should be vertex form of a conic section, but that's not what it is called. It is called standard form of a conic section parabola. So just keep that in mind as you're working through these problems. All right, now we're going to get into one of the examples. We're going to take a look at question number 1 together, and then you can do question number 2 on your own. So I'm going to zoom in here so I have that additional space that I'm going to need. Guys, with conic section parabolas, you're going to find it very beneficial to graph them. Once you can visualize what you're seeing, then it makes it a lot easier to solve this problem. Okay, so the focus is at 0, -8. That's down here. Okay, now I'm just going to sketch this thing. I'm not really going to be graphing it accurately. Now the next thing I'm going to do here is I'm going to draw my directrix in as well. Let me change the end behavior of my line segment. All right, and now that's going to be up here at 8. So my directrix is up here. Now what I know from the definition of a parabola is that the focus is on the interior, the directrix is on the exterior. So that means that the parabola is always going to open in the direction of the focus, and of course away from the direction of the directrix. Okay? Now in this particular exercise, you're going to be using the distance formula to write the equation of the parabola. So we are going to need this picture to help us understand what that's going to be. So the first thing I know is that this is the equation y equals 8. The second thing I know is that this is the ordered pair 0, -8. Because of the symmetry between a focus and a directrix, I know that the origin is the vertex of my parabola. The next thing I'm going to do here is, in order to use the distance formula properly, I need some value that is located on the parabola itself. But the thing about it is that I don't know what that value is. So what I'm going to do here is I'm going to start by calculating the distance from here to here. The next thing I'm going to do, and you can clearly see that this is a sketch, is I'm going to calculate the distance from here to here. And due to the definition of a parabola, these two distances are going to be equal. And since they are equal, that's how I'm going to get my equation from the distance formula. Now I have an ordered pair here for this point, I have an ordered pair here for this point, and I need an ordered pair here for this point. Well, at this point, I know that the y value is 8 and the x value is unknown, but it's going to be the same x value as this one because that is a vertical line. Now I have my 3 ordered pairs that I'm going to use in the distance formula, and now I can begin my work. So down here below, I'll start with my 2 distance formulas equal to each other, and let's just go ahead and start with these 2 points right here. So I get x minus x squared. Notice that cancels. Plus y minus 8 squared. Now that's going to equal this distance right here. So we're going to use in the second one x minus 0 squared plus y plus 8 squared. And that's because a minus and a minus makes a plus. Remember, the distance formula is x minus x, y minus y, so this is y minus a -8, and that's how I got the plus there. The first step I'm going to do is square both sides, because if I square both sides, I get rid of those radicals. Makes it a lot easier for me. X minus x is 0, so I'm not going to bother writing that one. I'm going to write this one as y minus 8 squared equals x squared plus y plus 8 squared. Now these are both perfect square trinomials, so now I'm going to continue on here by writing them out. So I get y squared minus 16y plus 64 equals x squared plus y squared plus 16 plus 64. And that's a y there. All right, I'm going to go ahead and leave the x squared here, and I'm going to move all of this trinomial to the other side. So minus y squared minus 16y minus 64. We'll line them up here so I can see what happens here. 16y minus 64. Now, don't forget about your x squared. I'm going to bring that down right away. Cancel, cancel, cancel. This one cancels. This one cancels. And now I'm left with negative 32y equals x squared. Let me jump back real fast so I can show you what the final version of this form is going to be. Right here. Notice it was a parabola facing downward, so we're going to use this one here. Y equals 1 divided by 4p times x squared. All right, so notice that the y needs to be by itself, so I'll divide both sides by 32, and that's going to give me my standard form. So it's going to be y equals 1 over negative 32x squared. And there's the standard form of my parabola using the distance formula. Go ahead and give number 2 a try. Just use the same process here, the same steps. Begin by graphing it above so you know what you're looking at, and utilize the distance formula to help you out. All right, we're going to take a look at one more before I finish up here, and that is going to be question number 3. All right, it says to identify the focus, directrix, and axis of symmetry of the parabola and then to graph it. These are the critical values that you're going to need in order to graph this thing. And I'm going to add one more in because we need this one in order to graph it accurately. And I want you to identify the reference points as well. And you're going to be doing that for all of these from here on out. If it is a parabola, that is a conic section, you are going to add reference points to your critical values as well. Okay? So the first thing I need to recognize is that this negative 2 is where the 4p is located. So I'm going to go ahead and write that over here as y equals 1 over 4 times p times x squared. Now I need it in this form in order for me to get the 4p, but if you can see it, you know that the 4p equals negative 2. It doesn't mean that I have to move it over here, but I'm going to, so that it's consistent. Divide by negative 2. Now what I'm going to do is I'm going to rewrite this over here so you can see how it lines up. So y equals 1 over negative 2 x squared. All right, so let me highlight it here so it becomes clear. The 4p is negative 2 in my problem. So that is the key to my exercise here. Now what we're going to do is we're going to pull that out and we're going to say 4p equals negative 2. And from there I'm going to solve by getting p by itself. So that means in my problem, the key for my entire problem is the value of p. And the p in this case is negative 1/2. So everything I'm going to do from the focus to the directrix to the axis of symmetry to the reference points is going to revolve around this value of p. Without that value, I cannot graph this thing accurately. Okay? All right. Notice that there is no h and k. There are no values next to the y. There are no values inside with the x. So that means that the origin is the center, the vertex of my parabola. So we're going to start there. Vertex. 0, 0. Now, because this is negative and because x is squared, the parabola opens downward. So I'm going to make 2 little marks like this to help remind me which way it opens. I'm not going to draw the whole thing yet because I don't know what the stretch or compression is. But I want to remind myself that this thing actually opens downward. Now the reason that is, again, is because x is squared and p is negative. Okay? All right. The value of p is the distance from the vertex to the focus and the vertex to the directrix. So this is going to be 1, 2, so that means I'm counting by 2's here, so that's 2, 4. So that means I'm going to go down 1/2, which is this teeny tiny distance right here. I'm going to go up 1/2, which is this teeny tiny distance right here. I'm going to draw in my directrix right there. And now what I'm going to do is I'm going to go ahead and fill in my reference points. My reference points are going to be 1, because reference points are P, is 2 P units from the center. So 2 times 1/2 is 1. So I'm going to go over 1 here, over 1 here. Those are my reference points. Now I have my stretch and compression. Now I can accurately draw that guy right there. Okay? So now let's go back in and fill in all of the missing information. The focus is an ordered pair. The ordered pair for this focus is going to be 0, -1/2. The directrix is the equation of a line. And the equation of my line this time is a horizontal line. So that's y equals 1/2. The axis of symmetry, A, O, S, is also a line, but it's a vertical line at x equals 0. My reference points are P, are both ordered pairs. And in this case, they're at -1/2 and over 1 and -1. So that means my first ordered pair is -1, -1/2. And my second ordered pair is 1, -1/2. And those are the critical values that you need in order to graph these things accurately. I'd like you to try question number 4 now, and then we will spend a little bit of time in class tomorrow working on the rest of these extra practice problems so that you get a good idea about how to graph these conic sections parabolas, because they are a little bit different than the quadratic parent function that you've studied so far this year.